Dear jury members, you may like to cheer up our participants. You are welcome.
Hello, I'm very glad to see you all here today. I'm very excited about all the teams because all the projects which made it to the final are of very high quality. All of them are very interesting. There is no weak project of all of these 7 projects. So I'm very excited to see your presentations. Thank you.
Yeah, hello everyone. I congratulate you to making this to the final. I have read all your articles, I have seen all your videos, and I can say for sure that this event is has the most advanced and interesting results that any other event that we had before. So I'm very glad about it. I want to wish you all good luck, and it will be very difficult for us to choose the winner, but I wish you all good luck.
Hello everyone. I just want said that I also read all your articles and watched the videos, and they are awesome. You already did a huge work, so I just want to wish you luck on CopterHack. All your projects are very cool, so just good luck for you.
Hi, my name is Alex, and I remember starting CopterHack 2017, and after reviewing this year's project reports and videos and articles, I have to say that CopterHack really grew up, just like all of us grew up a little bit for this last couple of years. So it was really hard to not put very high points for every team and for every criteria, but I made my best to make an initial judgment, and let's hear it now.
Okay, yeah. Good luck for everyone, and because any teams to prepare their interesting project, and I was very excited in seeing how we develop a product during the year, and all presentation very interesting, and good luck in presentation the final stage.
Thank you very much.
Thank you. Sorry, Len, I would like to stay also a little bit because I only 2 minutes ago have started YouTube stream. Sorry for this because I was not prepared. So I was glad to see all of participants and jury, and I'm looking forward to see your presentations because this level of projects of this CopterHack is very high, and let's see what you can show to us. And Elena, please repeat some words about CopterHack, just maybe 30 seconds, please.
Maybe, yeah, what is it? Yeah, CopterHack.
Yeah, just a little, and introduce teams, please.
CopterHack is international open source project competition on aerial robotics. In this year, we have 17 teams in the beginning of the contest, and only 7 of them reached the final. These 7 teams today represent 5 countries. These countries is Canada, Belarus, Brazil, India, and Russia. And finally, I think we are ready to start our team presentation. We wish you the best of luck. Please welcome our first team is C305. Are you ready?
Hello, everyone. Yes, we are ready. Can you hear me?
Yeah, let's fly then. You can start.
Okay. I cannot demonstrate my screen. How can I demonstrate the presentation?
Please try now. I have
Okay,
made.
yes, thank you.
Okay, go ahead.
Can you see the presentation?
Yes.
Yes.
Okay. Hello, everyone. My name is Sergey Filimonov. Our team is C305, and we are glad to present you our project that is called UVB Navigation System. So what is the problem that we are solving nowadays? There are very few accurate, convenient, and low-cost indoor positioning systems. Optical flow and Aruka market systems are used generally, and positioning systems based on optical vision have a number of important disadvantages. In first, we need a constant good lighting and clear line of sight to get this work. And in second, a good camera that gives a clear picture and good positioning results usually has a high cost. Also, drone flight speed is limited due to camera frame rate limitations, and image processing leads to high energy power and computing power consumptions. So the idea of our project and our goal is to develop an open source system, positioning system that is based on ultra-wideband models. Ultra-wideband models systems have a number of advantages. The first is that the lighting level is not essential for this system, so the system can work in environment with any illumination and any visibility levels. The second is low power consumption compared to optical systems. At the same time, such systems provide a fairly high accuracy, and also the systems are very easy to deploy and use for users. You need just to place UVB models wherever you want, and it is good to go. So while working on our project, we had three main tasks. The first task is to develop UVB models that will be directly involved in positioning process. For these models, we needed to code firmware and create special casings for this model so that we could place models in a flight zone. The second task is to develop a ROS package for Raspberry Pi that will get positioning data from UVB models, process this data, and then send calculated position to a flight controller directly. And the final task is to perform flight tests to ensure our system works and estimate its accuracy and flexibility. In our system, we have two primary types of models. The first one is called anchor model. You can see this on the first picture. This model is placed in a flight zone where it flies statically and plays a role of a radio beacon to estimate the distance from. The anchor model has a special casing with a built-in power model. You can see the power model on the second picture. And this power model is powered by a single battery. The power model is connected with UVB board using a micro USB cable. The second model is a tech model, which is attached to the drone and is connected to the Raspberry Pi on the drone. The tech model calculates distances to anchor models and sends distance values to Raspberry Pi to then calculate the drone position. What about ranging algorithm? In our system, we use a double-sided two-way ranging algorithm to find distances between UVB models. The main advantages of this algorithm are clock synchronization independence and high accuracy of time of flight estimation that is achieved by two-sided delays calculation. The distance measure is done via estimation of time of flight of the signal between two models. As you can see on the right picture, this is done with 3 message transmission. The device A sends a polling packet to device B, and then device B responds to device A with a response packet. And after getting the response packet, the device A sends the final packet to device B. Calculated delays between packet sending and receiving on the both sides are used to calculate an estimated value of time of flight. This is T propagation of the picture. After calculating distances, we send the distance values to the Raspberry Pi, where we can calculate final drone position in UAV model's coordinate frame. Knowing anchor models positions and distances to them, we can use a trilateration algorithm to estimate the drone position. As you can see on the first picture, we are finding a point of intersection of spheres with known centers and radiuses. To solve this problem, a system of nonlinear equations of spheres is formed and solved. After solution, the calculated position of the copter is then published to flight controller using the Mavros vision position topic. On the right picture, you can see a visualization of our system in RVs. There are 4 anchor models on the ground and a big red arrow in the air that shows the estimated drone position. We have performed a couple of important flight tests to ensure that our system works and estimated accuracy and flexibility. First of all, we tested the ability of the drone to hold exactly one position in the air. And there is a video of the test. So this test shows that position estimation error is not really big, and it is about 10 centimeters. Secondly, we tested the ability of the drone to fly to the specified coordinates. To begin with, we tested the ability to simply fly 5 meters forward. This is the first video. And also we have tested the flight on a more complex trajectory. We have decided to use a square trajectory to this. This is the second video. As a result of our work, we have made a firmware for UAV models, 3D models for UAV models, casings, trilateration software package for Raspberry Pi, and documentation for our system, which you can find by following the link below. The characteristics of our system is a precision of 10 centimeters, ranging distance of 40 meters per model, a working area of 5,000 square meters per 4 models, and a cost is about $90 for a minimal setup. And this is all. Thank you for listening.
Thank you very much. Yeah, it's very interesting and well done. I have the first question about high. Do your system works in 2-dimensional or 3-dimensional space? What about
Our
height?
system works in 3-dimensional space.
So the height of flight you also detect by models?
We can detect height of flight using our models, but it has lower accuracy. So for now, we're using distance. Distance sensor.
Yeah.
Yes.
Rangefinder, right? And
Yes.
and what is the lower accuracy? What is the precision? Is it the same 10 centimeters or lower?
No, it can be up to several meters for the height.
So 10 centimeters to the X and Y coordinate, and
Yes.
several meters for Z coordinate.
Yeah, but that depends only on the placement of the tags, anchors. Yeah, so if we distribute anchors by the plane, we get high quality of positioning for X and Y axis and low quality for Z axis. If we will distribute anchors vertically, we will get higher quality for Z. So it's just because we need to distribute the anchors another way, and it may be not convenient in usual room to distribute sensors on ceilings and so on.
We must place anchors on different height, but we didn't test it placing on the really big height. We tested it with height of anchors of 2 meters maximum. So I can't answer the question. I can't state that if we place anchors on very big height, the error for that coordinate will be low.
Okay. I understand this. Thank you. And I have a second question about the numbers of models. You use 4 models. What if I will use 5 or 6? So 4 it's a minimum number, right?
4 is a minimum number.
Minimum. So if I use more models, the precision quality will be better, right?
It will be better, and we will have a much wider working area. Yes.
And what about your software? Do your software ready for this or not?
Our software it supports yes, it supports much more backends. Like for now, as I remember, it supports 10 backends maximum, but this can be much more wider. So
okay.
It is not limited.
Okay, and the last question from me: do you have some limitations about area, about walls, ceiling, floor, and so on? Any interference of radio signal? Is it problem or not?
This is not a problem. This is not affects much the results of estimation.
So if okay, and if I have 2 rooms, not one big, but 2 rooms, and the wall between them, can your system work or not? Or
yes, it will work.
It also works. Okay.
The obstacles doesn't affect much for our system.
Okay, sounds good. Thank you.
Thank you. Andrei, you can ask a question.
Continuing the question about larger amount of anchors, you chose two-way ranging, and while it's the easiest and the most robust method of operation, DW1000 supports other modes of operation, including time difference of arrival and other slightly different modes, which are better suited for large number of anchors. So if in your scheme we will increase number of anchors and we will increase number of drones, then the number of combinations, so each drone must query each anchor, and it will very fast lead to very high latency. So have you considered other modes of operation? Thank you.
as I
So
understand.
this solution is very good for a limited number of anchors, yeah?
Yes. For more number of anchors, I think this will be good as well. We didn't test with another methods of range finding, and we have used only DSTVR method. I think this won't work in our implementation for a higher number of drones, because for our system there can be only one tech model that should be placed on the drone. So there should be only one drone in the system for now. But I don't think there is any limitation for anchor models.
Okay, so yeah, if you want only to support one drone, it's not really a problem, but don't you have in plans supporting several drones flying simultaneously at one time?
Yes, we have plans to improve our system and support more drones.
Okay,
I think it is implementable using DSTVR, but maybe we will use another method.
Yeah, but you see, if we have 100 drones and 100 anchors, then you need to perform 10,000 of rangings to estimate the position using your scheme, and only 100, so 100 times less. If you use time difference of arrival or other simpler scheme, but which is harder to implement because it requires to synchronize the anchors. But if you want to introduce large number of drones and large number of anchors, this the complexity, the number of calculations will rise as second x squared, yeah, second order. Okay.
Thank you. Next question from Oleg Kalachov.
My question is, how do you think, how is your solution is close to become a real product that you can sell and that our users can buy and use? And what do you think about the cost? And do you have any plans on that? What do you think about the total costs for user on your system complete? And how much time an average user will have to take to get the system work from scratch if he buys it?
Yes, we have thought about publishing this as some product, and we have
example.
Yes, as an example of such a product, it is a POSIX system, which is really similar to our system, and yes, and we maybe will publish that as a product, but we need to improve our system, of course, and we can improve precision, and we can improve our system to use several drones. What I said before. It is our system, answering on your second question, our system is really easy to use, and the user can deploy this from scratch in about 10 minutes or 20 minutes maximum, I think.
And what do you think about the final cost for the user of what everything that he needs to set it up, excluding the drones?
The final cost of our system is, as I said on my last slide, self cost of our system is about $100, so maybe it will cost $200 or $150. So in this range, I think.
No, you should be selling it for 1,000. Okay, if it costs $100,
it depends on who. It depends on who to sell. I think
this is how it works in America. Like the guys like you put together an open source project and sell it for like 10 times more expensive. Okay.
Okay.
Yeah. Or trying to sell, marketing it wide, and then they're finding number of customers around the country.
Okay.
Sell it with like 1,000 per.
And since because I think that since our drones is quite popular, your product might have some success because I believe that users are interested in wideband position for the drones. Also, my another question: the video that you showed us, the drone uses only your ultra wideband system to position because it has the camera installed, but it doesn't have camera positioning, right?
Yes, it doesn't use camera. We just didn't detach the camera from the drone, but the drone didn't use the camera.
Mm-hmm.
It used just our system.
Okay, thank you.
Are there any questions?
Okay. One more question. Do you have any test of your solution in the outdoor? Because especially in Far East hills or mountain condition.
We didn't test it in outdoor because it's usually in outdoor the GPS systems and the RTK systems are usually used, but I think we can use our system in outdoors as well as in indoors navigation.
Okay, thank you.
There is no difference, I think.
Thank you. Next question from Alexander Fomenko.
So I might have missed, what rangefinder are you currently using to detect the altitude?
This is a default rangefinder of Clover.
Okay, LiDAR, right?
Yes.
Okay. Thanks. And what about walls and surfaces penetration? Did you test that? Signal penetration. So I mean, if the drone flies behind something, behind an obstacle in relation to the beacon.
Of course, the walls and obstacles do not affect really the navigation system for UVB.
Really, like even concrete, even like steel and forest.
We didn't see that in our test.
And okay, thanks.
Thank you. Next question from Alex Chukov.
Hello, thank you for your presentation. Actually, I have one question as a user. Imagine I come in empty room. What time it takes to deploy and set up your system to make my drone fly in this room using your solution?
Yes, as I said before, this will be about 10 or 20 minutes.
And it's from start to the good flight, yes?
Yes.
Oh, okay. That sounds great. Thank you.
I mean, it sounds nearly impossible. I can't imagine that something as hard as this can be set up in 20 minutes.
Yeah, I remember how we use POSIX, and it was not 20 minutes. It takes an hour to get good position and a lot of time to set up height of marker of beacons and etc.
If you have successfully installed 100 times another installation, so the 101st will takes you 10 minutes because experience matter.
Yeah, makes sense.
I think final question from Alexander Fomenko.
Yeah, can I have your business card?
What?
Actually, all the articles are published, and there are contacts in the articles.
Yeah, I know. It's just interesting because I can see how your system can support the drone operations in the company I'm currently working for. Because now we're using a combination of GPS and optical systems, and then we're looking for night flights, and this is all we're looking forward to. So thank you. That was awesome.
Thank you very much. Next participants is MoCap Clover. Please take the floor.
Hi, can you hear me?
Yeah.
Okay, great. Just let me know when I can share my screen.
Okay, please try now.
Okay, yeah, that seems to be working. All right, hello everyone. My name's Sean, and I'm a master's student from Dalhousie University in Nova Scotia, Canada. And today I'd like to just give a brief overview on the fundamental components of my project. And if you have any questions, you can ask me at the end. So yeah, this is just a brief overview on my project. I'll kind of go over the hardware setup. So it's basically setting up the motion capture system with the Coax Clover platform. And then I'll go through some of the data transmission and communication protocol. And then I have a few examples that I implemented in my educational document involving PX4 auto tuning. So auto tuning the control system on board, and then a complex trajectory tracking example that can be used in simulation and hardware application. So yeah, you can see in the lab that I have at my university, I have a Coax Clover drone that I made some modifications to. At the bottom there, I attached a rigid gripper mechanism that I used for aerial low transportation tasks. And for these tasks, I needed highly precise pose feedback for both the drone and the target object. And you can see the gripper mechanism also blocks out the camera's field of view, so it wasn't very useful to use the marker system. Because of that, and the fact that we have a motion capture system in the lab, I transitioned the computer vision one to the external camera sensors for pose feedback. And I thought it would be a good idea to provide an educational document for Clover users because the motion capture system is a pretty common application in research. And although very expensive, it'd be very useful to kind of know how to set that up with the drone. So this is just the basic setup that I implemented in the lab. It's pretty simple, just a 4-camera setup with a pretty small volume, which was sufficient for my applications. Includes 4 cameras, a ground station computer running Motive software. So that's used to stream the pose data of the drone and offer it to whatever other sources. And then I also have my own laptop that I use for complete system analyzation. In my document, I talk about how to set up the cameras, how to position them, how to calibrate the cameras, and also how to set the software settings so you can stream pose data on a certain IP address that you can access from other sources. And outside of the actual cameras, we have the target hardware, which is the drone. That consists of the flight controller, which is the brain of the drone that's responsible for controlling and positioning it. And we also have the Raspberry Pi, which is basically the high-level command system used for onboard computing. And that's where all the different commands take place. And yeah, on the Clover, I use the PX4 firmware, and with the in my ground station computer, I run Q-ground control. So in my educational document, I talk about how to configure the firmware and configure certain parameters to accept data from the extended common filter or from the motion capture system, sorry. And yeah. A few other components that are important. In order for the cameras to detect the drone, requires you to mark it with certain reflective markers. You can see in the figure there, I have 4 reflective markers. You can use any amount from say like 4 to 12, but it seems 4 or 5 seems to work well enough for this drone. They have to be set up sort of in an asymmetrical shape so the software doesn't get confused on its orientation. And what you do is you create a rigid body, and I talk about how to do that in my educational document so that the system can actually track the drone's position and attitude. So yeah, this is just an overview on the framework architecture or the data transmission that you would, I guess, would set up if you followed my educational document. So you can see that the cameras, they provide the post feedback for the ground station computer. And then in my setup, I use an external system. So you can use your laptop or a computer, and you can run, say, the virtual machine that Clover provides or any kind of Linux system. And so what I do is I set up a VRPN application on that system, and it connects to the ground station computer's server, and it can stream the pose data via UDP. And then I'm able to transition that to the Raspberry Pi over a ROS network. So ideally, I wanted to transition that data directly from the ground station computer to the Raspberry Pi. However, a lot of the applications are not able to be built easily on the Raspberry Pi due to architecture issues. But yeah, I was able to work around that, but I'll talk about that in the next slide. And then I eventually remapped that data to the Vision Post pipeline for access to the PX4 flight controller. So yeah, like I said, the ideal situation was transitioning the data from the ground station computer to the Raspberry Pi. I wasn't able to do that with most open source applications, but I coded my own C++ UDP connection, and in one click of a button, it'll transition the data to the Raspberry Pi and remap it to the flight controller. I just wasn't able to generalize this to any kind of motive software version because I hard code the version in the software or the application, but in the future, maybe I can generalize that for any Clover user or setup. So yeah, now that we have a well set up localization method, another issue is tuning the drone. I know Clover does provide gains that fly well enough with the drone. However, for my setup, I added a gripper and a few other components that had changed the mass moment of inertia of the system. So retuning was important, and it's also a good idea to have a well-tuned drone. So I provide basically a step-by-step analysis on how to use the auto-tune module provided by PX4, which is to improve upon the tuning of the inner attitude and angular rate controllers. And I know many people may not have a very sophisticated control background, so that makes manual tuning even more difficult. Even for someone with a control theory background, it's quite challenging and tedious to get it to work well. So that's one of the benefits of using this module. On the right there, you can just see that gives a kind of an overview of the theory. It's basically an indirect model reference adaptive control module that uses some system identification and then tunes the gains based on a few set parameters by the user. And these set parameters, I talk about how to define those in my document. The two main ones include the rise time, which is basically how fast it will react to the inputs, the step inputs, and then and tune the gains based on that. And then the other one is just the amplitude of the step inputs. So you can just set that large enough so that you actually notice the step input during flight. You can see there in the figure, that's what it would look like during the auto tune process. So yeah, with a well-tuned drone, the next kind of application I wanted to implement was complex trajectory tracking. So I coded an application that allowed the Clover, both in simulation and hardware, to track a smooth figure-8 trajectory represented by the equations there on the right. So it's position with feed forward velocity, feed forward acceleration, and yaw rate. And because this is a smooth trajectory, all those, they're all available. And yeah, you can kind of see there I implemented in simulation just what it would look like when using the application. And I plotted the trajectory on the left. The poor tracking, that's just for my research because I implemented the tracking under heavy disturbances with different control methods. But that just illustrates the what the trajectory would look like in the X, Y, and Z dynamics if you were to implement it. And yeah, those are the two main applications with the motion capture system. However, those are pretty basic, and there's quite a wide range of different robotic applications you can do with indoor flight and the motion capture system. In my research, I implemented sort of pick and place tasks you can see in that video. But yeah, there's so many other different cool applications you can do when you kind of have a good localization method for indoor flight. And I kind of talk a bit about that in my educational document that you can read through. But yeah, possible future implementations. I mean, I can improve the simple off-board trajectory generation model just for general applications, hardware in the loop simulations, and maybe an educational setup for the UDP data transmission framework that I talked about before. But yeah, that's the basis of my project, and there's quite a bit more other details, but if you have any questions, just feel free to let me know.
Thank you.
First of all, before we jump into questions, I have to say, you said it's basic, but don't be shy. I mean, it is basic, but it has potential. It looks like it has potential to be improved, so don't just call it, oh, we're basic, like, no, we're great.
First question from Andrei Krygotsky.
Yeah, thank you for great presentation. You showed us plots of position versus set point in simulator. Yeah, yeah, this one. And do you have such plots for real world flights?
Yeah, I mean, these ones are from the plots are from the real world flights. I haven't run the plots for the, I don't have the plots for the real world figure 8 tracking. However, I have plotted it in flight log analysis, and it's basically the same. And also these plots are for, I was implementing the PID controller, which is the basic control system with PX4. I also implemented my super twisting sliding mode controller and higher order sliding mode observer under significant disturbances. So the basic idea was just to show what the trajectory looked like, the set points or the reference in both the XYZ dynamics. But yeah, plotting it is pretty simple. Yeah.
Okay, thank you.
Second question from Oleg Kolachov.
Yeah, thank you. I have two little questions. The first one is, I haven't seen in your article. Have you maybe compared the precise of this system, motion capture system, versus the our marker positioning system, and how marker positioning system is worse than yours?
I mean, I haven't made like direct analytical comparisons. I made like eye level comparisons. I can see the stability of the drone is a bit more, I guess increased with the motion capture system. But theoretically, the motion capture system provides like accuracy for the pose on position under a centimeter and attitude under a like a degree. It's very, very precise. I guess it just depends on how well the drone handles that pose feedback. I mean, it can only be as precise as performance allows it to be. But I wouldn't say I made direct comparisons on the marker system and the motion capture system. But theoretically, it would be more obviously precise.
Yeah, because now when you have so precise system, we now can actually know the precise of marker system because you have very precise feedback. So you can you have very precise ground truth, and you can say for now that our marker system precise is this number, I guess.
Wait, Oleg, you didn't know your marker system precision?
You know, we don't have such, unfortunately, such a cool motion capture system. We wanted to have it, but we don't have. So our numbers about the precision of our system is not so so good, so precise.
Not under centimeter, right?
Yes, of course, it's much worse. And the second question, you said you performed auto tuning, and have you published the results you got from, I mean, the PID parameters and so on?
I don't think I auto-tuned my rigid gripper drone, so the gains may not work as well on like just a normal Clover without all these modifications. But I did go into quite depth on how to do the auto tuning with the Clover, and I would say it's pretty straightforward. You can do it with, you don't need a motion capture system. You can do it with the marker system or anything. You just put it in position mode and set the certain parameters and then activate it and it'll tune it. So I mean, it would take pretty limited time to actually get those gains. But yeah, the gains in my drone that I auto-tuned for probably wouldn't work as well for another Clover.
So you maybe will publish it in your okay, thank you.
Next question from Oleg Kumpirenek.
Yeah, thank you, Sean. It's very well done. But what's actually precise of the system? In your article, I see something like 3 millimeter, right?
Yeah, I mean, just from the website on the OptiTrack motion capture system, it's very like precise. Under a degree, like point some degree in pose or attitude, and the positioning is very low as well, around a centimeter or so.
And what about the maximum size of cube you can control with the system?
Like the volume that I can create?
Volume, yeah, volume.
I mean, like I have 4 cameras there, and I don't know if I have 4 cameras here. It's a pretty small volume, but like as systems become pretty advanced, you can use a very large amount of cameras. The other research team in our lab, I don't know if you can see in this figure, but in the very back there in the corner, you can see those small blue cameras. So they cover the entire basically lab with theirs. There's 4 corners. The 3 of them aren't available, but they can cover the entire volume. And for indoor flight, the volume is not very limited. It depends on how many cameras and how powerful the cameras are. But the volume can be very large for most indoor applications. I don't know what the cap limit is, but I've seen some setups, especially with like MIT. They use a motion capture system to do like very high level, fast paced drone tracking. And it's like a massive facility, and it's all with the motion capture system.
Yeah. Okay, and the other question is, when you do the system, have you seen some other teams who make same thing with PX4, or you have made it from scratch?
Oh, there's one. I mean, with the control system.
Yeah, OptiTrack is PX4.
Yeah, there's another student on the other team who uses another like Pix Racer with PX4. We also have Crazy Fly drones. So it's like the control system's very limited. It just has like attitude control, simple attitude control, PID attitude controllers on board, and then they run position control and everything off board. So it doesn't use PX4. PX4 is not like needed, but it's convenient to use with the motion capture system.
Yeah, and what about your ROS package for option track? Is it
I think the VRPN, I don't know where it slides at. Yeah, the VRPN package, yeah, you download that from, it's like an online sort of GitHub. I discussed on how to download that, set it up. But like I said, that was application was for was my initial setup because I couldn't figure out how to directly transfer the data from the motive computer, which is the ground station computer streaming the data to the Raspberry Pi. So you can just download that on your laptop and stream the data to your laptop and eventually transfer it to the Raspberry Pi over a Rust network. But like I said, I recently coded my own C++ application that uses a UDP, and it's directly onboard the Raspberry Pi and transfers the pose data to the Raspberry Pi and remaps it to the Vision pose pipeline. That is on my GitHub. I didn't really create a educational setup on that because I had to hard code the motive version in my code, and it wasn't, I guess, generalizing that for any Clover user or any researcher is not simple. But that's like a future application that I look to do.
And when you send data, what protocol do you use?
Well, it's UDP from the ground station computer to your computer using VRPN and then transfer it over a ROS network, so like a TCP. But the C++ application that I coded, it's a direct UDP transmission from the ground station computer to the Raspberry Pi and then remap it to the Vision pose pipeline.
Okay.
Yep.
Yeah, it's clear. Okay, thank you.
And final question from Alexander Fomenko.
Yeah, so as I could learn from your article, you're a research student, right? You're a grad student. So can you give me examples of research applications which were mentioned in the article that can benefit from your proposition of the system?
Like just this system for like a
what
general
kind of
application?
research? Yeah, like, or maybe like the reasoning for you being interested in this project from the start, like how?
Yeah, well, I mean, low transportation. Yeah, like I mean, this, in terms of transitioning the system, I believe, yeah, like I said, I needed precise pose feedback of not only the drone but the target object. So I was doing pretty simple pick and place tasks. So I would put actually OptiTrack markers on the target object, so it allowed me to know the position of the drone and the target object. But yeah, so that was the motivation for transitioning the markers to the motion capture system. But the motivation of my research is handling certain disturbances with the control algorithms on board. So PID is pretty poor handling varying disturbances like payloads, wind disturbances, where I implement a robust nonlinear control method to handle those disturbances, and it improves the performance quite significantly. But with the motion capture system, it is very popular in research because it eliminates the worry about localization. Because if you're interested in a certain area of research, whether that's certain control performance or certain, I don't know, tracking performance, you don't want the localization being a limiting factor. So with the motion capture system, it provides very good performance in that aspect, and you don't have to worry about whether, I don't know, localization was poor or something like that.
Yeah, you mentioned wind disturbances. Is your system capable on working outdoors?
I believe there's some, the motion capture system has been used outdoors in certain universities. However, it's most commonly used indoors, just because that's where it's usually performed or where it's, I guess, operates in.
So so it's not functional like on the very wide areas, right? So the range is limited by resolution, I believe, right, or something.
It depends on the cameras and the setup. You can have like any amount of cameras, and yeah, as long as it's, I believe, as long as the rigid body is recognized by at least 3 cameras, it can extract its pose. But yeah, there's cameras that are very expensive and can track very large volumes available. So yeah, it's not for like most indoor applications, it's not limited. You're not going to need a larger volume than it's capable of.
Thank you.
Yeah.
Thank you very much.
Thank you.
And next team is DJS PHOENIX. Please welcome.
Hello. Please enable screen sharing.
Hello. Oleg, could you please give access for sharing screen?
Yes, I'm here. Who is needed the access?
I.
Okay. Okay, please try now. Okay, we can see your presentation. Thank you.
Hello. Namaste and good evening to one and all present over here. I am Shruti Shah from DJS PHOENIX, the official drone team of DJ Sangvi College of Engineering, situated at Mumbai, India. We are a team of passionate undergrad students who love to design, analyze, manufacture, and assemble drones. We want to show the world what's possible with our flying machines and to use it to solve real-world problems. Moving to our project, Cheta, the autonomous racing drone that can navigate through complex courses at high speeds. Our drone is equipped with autonomous navigation, precision flight control, real-time data analysis, and an automated safety feature. The autonomous racing drone not only benefits individuals, but businesses and society as a whole. Now, my teammate Vedant will brief you more about the idea of the project.
So, the idea behind the development of autonomous racing drones is to combine the excitement and competitiveness of racing drone with advancement in autonomous technology. Our drone has been developed to help individuals with little to no flight experience so that they can operate drone with ease. Autonomous racing drone aim to take this excitement to next level by removing the human element and showcasing the capabilities of advanced autonomous systems. They serve as a platform to test and compare the performance of different algorithms in a thrilling and competitive environment, while pushing the boundaries of what these drones can achieve. Now we move on to the manufacturing processes involved. First step involves designing the drone structure, keeping in mind the aerodynamics and space required for various components with the help of SolidWorks CAD software. Second step involves finalizing the appropriate material for the frame, that is carbon fiber, which is lightweight and highly durable. For making mounts for camera and other electronic components, we used PLA, which was high in strength and shock absorbing capabilities. We also had to ensure that we do not exceed our budget at any instant. Final step on mechanical side involves buying the appropriate frame and 3D printing of the mounts. Now my teammate Omkar will provide further explanations.
So here are the softwares that we use from designing to making our drone autonomous. SolidWorks. We used it to design the CAD of our drone and simulate it to check the integrity of components. Gazebo. Gazebo provided us the realistic simulation platform where we tested the overall system behavior before deploying them on real hardware. Clover. We used the ARPA image provided by the Clover and Clover platform to simulate our drone in Gazebo. We used it QGC. We We used it to calibrate various sensors and plan our autonomous mission by configuring various mission parameters. Now we move on to the workflow of Chetak. So as you can see here, at the center, it is a Clover platform that helped us to make our drone autonomous. From process 1 to process 4, it is all about the configuration part, where we started from downloading the firmware, then flashing the image into the SD card of RPi. After that, we set up various QGC parameters to the required values. Now, from process 5 to process 8, it shows how our drone actually works. Initially, we access the camera and our drone is ready to launch. After that, we search for Aruko tags and do data processing. We also use OpenCV for detection of gates. And all this data accumulation and data processing helps our drone to navigate through gates smoothly. Now, my teammate Harshil will explain more about the coding department. Over to you, Harshil.
Thank you, Omkar. Now here's the basic breakdown of how Aruko markers are detected. The first step, generating. Aruko maps are created using the Aruko library from the Clover quadcopter platform, which provides tools for generating and detecting the patterns. Then comes printing. After generating, it can be printed out and placed in the environment where it will be used for tracking. And after that, capturing. A camera or other imaging device can be used to capture images of the Aruko map. Last but not the least, tracking. Computer vision algorithms can be used to detect and determine the position and the orientation of the camera. Now I'm going to brief you about how the code works. So we imported necessary modules and packages from Clover quadcopter module, which was provided by you. We then move on to define the speed and rotation variables for the drone. Next, we define functions to move the drone to a given position and rotate the drone. We then initialize drone's position and orientation arrays. We then take off the drone using a service proxy. Now, the heart of the code, which is inside the loop. We capture an image and convert it into a NumPy array. We then go on to detect the fiducial markers, which are the Aruko markers in the image. We extract gate IDs from the detected markers and store them in a list. We estimate the position and orientation of each gate. We then calculate the direction from the drone to each gate. Then calculating the angle between the drone's direction and the gate's direction, we check if the angle is larger than a threshold. If it is, then we rotate the drone towards the gate until we find a marker. Otherwise, if no gates are found, we land the drone and we break the loop. Now, here's the simulation of how our code works. Now, as you can see, it has started to detect the Aruko marker, but the orientation is a bit off because it's on the left-hand side. So it tries to orient itself towards the gate, and then it moves towards the gate. Furthermore, as soon as it detects the second Aruko marker, it is going to print in the console log. This shows how efficient our code is and how fast it can detect Aruko markers within the given threshold. And finally, if it does not see any Aruko markers, it just lands. Now on to Suhasi, who is going to explain the electronics part of our drone.
Thank you, Harshil. Coming to the power distribution part, once we switch on the battery that is connected to the input of a flight controller, it starts the process of power transfer. From the battery, the power is transferred to the flight controller, which is further passed to the power to the Raspberry Pi as well as to the 4-in-1 ESCs connected. We have connected the OAK-D light camera on the ports of the Raspberry Pi. So once the power is received on the Raspberry Pi, the camera too is powered by it. Similarly, the motors are connected with the 4-in-1 ESC. So once the ESC receives the powers, the motors too receives the powers after it, and they start rotating. Now let's discuss about the data transfer. After the drone starts its flight, that is, after the power transfer is done to all the components, the component starts performing its application of data fetching and transferring. Firstly, the camera detects the Aruko markers and transfers it to the transfers the image information from Aruko markers to the Raspberry Pi. Raspberry Pi then transfers that information to the flight controller to decide the route of the drone accordingly. The flight controller is finally transferring the information signal to the ESC, and the ESC controls the motors to make them run as per the path decided. Now, I would like my friend Madhura to continue from here.
I'm sorry, we can't hear you.
Hello, can you hear me now?
Yes, we can hear you now. Please go ahead.
As we had expected, in the course of making this project faced quite a bit of challenges. In the first month itself, the selection of components was a tedious task. The budget itself proved to be a major constraint factor. However, after a lot of research, we were able to find the items which fit within our budgets. We are a team of undergraduates, engineering undergraduates. Owing to our end semester exam towards the end of January, we finished our monthly deadline. We finished our monthly task with a stretched deadline. Debugging of the neural network took us a couple of days. Now my teammate Jeet will give us an overview about the budget.
Yes, thank you, Madhura. The expenditure was one of the challenging tasks for us as we were making it yet another time and had to build it with comparison to the previous one. After comparing it with the previous budget and also referring it with the people who have already built this autonomous drone, we decided on upgrading the components and getting updated with the technology. Thus, we raised our budget and found finest and reliable products, and we made it at a cost of rupees 40,572 in INR, and when converted in rubles, it cost 39,455. Here's a short video to conclude our project. Thank you. And now we are open for questions.
Thank you very much for this great presentation. Well done. And please tell us more about demonstration. The last video, has it performed fully autonomous, right?
Yes. Yeah, it's fully autonomous.
Okay. And what about precision? Is it was good from the first try or not? What was the failure rate and so on?
Yeah, it wasn't good from the first try. So we faced many difficulties. So while first starting, the camera position, the camera was like starting to look very heavy for the drone. So while the drone was flying, it wasn't able to detect the Aruko markers properly. And sometimes it used to go very high up and used to hit the gate itself. But over the time, we perfected it, we tried to do it. And then to prevent more damage to our drones, we created a fail-safe feature, which like we had a button or remote, which automatically, disconnects the battery from the drone itself. So over a lot of tries, we were able to achieve this final video.
Okay, good. But this final success try was only one, or do you have some statistics of this result in what is the success rate or failure rate or something like this? How good does it work? How stable does it work?
Okay, so currently we have only tried it twice. So like, okay, not twice, but we have like tried it around like 10 times. And around the 10 times, after making consistent changes, we were shown promising results. So we weren't able to simulate a lot more because of our time constraints and everything. But around 10 tries, there were 3 successful tries with, no damages, or the drone wasn't, thrown off the trajectory or anything. It landed perfectly, took off perfectly, and it went through the gates at the proper speed.
Okay, and this gate was placed on the one straight line. But what if you have some turns, curves of gates, for example, turning left or right? Will it work or not?
So for that, yeah, so the simulations were promising. So we placed the gate at an angle to it. The code itself used to like correct itself, and the drone used to align the position of it towards the gate. And we have tried it, and it did work. But there were some technical errors because when you try to embed the system in the IoT, like in the hardware part, there were like the data loss and transmission was there, due to which it did crash in the start. But yeah, we were able to make it work. It is able to turn, but it is not able to turn after a certain point of angle.
Okay, thank you.
Thank you. Second question from Andrei.
Yeah, thanks for your presentation. Could you tell us how do you land in autonomous mode? So do you transfer the mode to landing mode, or do you land it in offboard yourself?
Oh, so in autonomous, could you come again? I did not get your question.
Yeah, how do you perform landing autonomously?
Landing, okay, yeah.
Yeah,
So,
what mode of landing?
So as long as there's a threshold, we have given a radius. If in a given radius, it does not detect any Aruko markers, the drone will perform the landing. The speed and the velocity of the motors will decrease itself and will just go down at the position where it was hovering.
And is it in land mode of PX4 or in offboard mode? Is it offboard mode?
Offboard mode.
Offboard. Yeah. Thank you.
Thank you. Next question from Alexander. Alexander Fomenko, yeah.
Oh yeah, sorry. So no GPS is involved, right? Hello.
Yeah, no GPS.
Did you hear me? Okay. So the question is, first, what speed you can achieve? How do you think that? What is the maximum velocity or speed you can achieve in this setting?
So currently the maximum speed which I've achieved right now is 25 kilometers per hour. We haven't been able to cross the threshold 25 kilometers per hour because if we do that, then the detection of the Aruko markers will be hindered and the drone won't work properly. So right now it's 25 kilometers per hour, but when we incorporate more technologies, when we have more resources, then we can increase the speed because we can use better algorithms and we could use deep learning instead of Aruko markers. So it will like process itself and it will go on a feedback loop and it will learn itself and the drone will progress faster.
So this project is about racing, right? So it is when 2 or more drones are involved, right? So what is this competition about? So who competes? 2 teams tuning and configuring the drone, or what is the purpose of the putting your technology into a race? So how's the competition look like?
Yes, so like there's an IDRL, Indian Drone Racing League. So it hosts competitions like for FPV drones, for manual drones. So coming up with an optimistic idea or plan. So we thought of a collaboration with the IDRL or planning to keep workshop for that. So if it goes well, so we thought of keeping off drone kits for ourselves and then keeping the coding or coding workshops for how to like code through Clover platform, and then we can give them a track and perform race events.
Okay. And my last question is there a semi-autonomous mode where the pilot can control selected channels?
Oh, we haven't incorporated the semi-autonomous mode yet. We have tried to make it fully autonomous. From the Clover toolkit which have given us, we have utilized it fully to develop it in that. But yeah, One of features we provide is like through the camera, we can connect it to the VR goggles. So a person who has no piloting experience could feel the rush of how to pilot the drone. So that's what we were aiming at targeting.
Thank you.
Thank you. Next question from Oleg Kochev.
Yeah, I've checked out your article and your documentation, and I actually maybe have not found the link to the source code, all your source code. Maybe it's there, or maybe there's a page called flight code. Is it the whole code, or it's only part of it?
So basically, it is the part of it. All the services we have been pushed into the GitHub repo, so you can check over there. It is a part of the flight code which we have done in the GitHub. Yes.
So you have your code on GitHub published or not? Because I still don't get it. If you have it, then you please, maybe you will publish it to our chat. The link.
Sorry, there was just a disconnection. Yeah. So basically, the GitHub repo we have provided, in that all the services and processes we have mentioned, and in the GitHub book which we have provided the link. In that there is a small part of our code, which is that Py file is going to run, and all the services are going to run up behind it.
Okay.
Okay, one more question from me. Do you have any plans for further develop your projects to increase speed or make a real competition between two drones, maybe one drones and some main pilots? What plans do you have for the development?
See, basically we haven't used the deep learning model. We have just provided the coordinates and everything in the NumPy array, and we are providing and the drone basically is following that. So we are going to learn about more about the deep learning model and provide the feedback mechanism and something, so that we can increase the high speed and accuracy for that.
Okay, thank you.
And final question from Mikhail Smirnov.
Okay, it's very little question. If I'm correctly understand, your decision works just with Aruka marker, or maybe I'm not correct understand. What about the work without the Aruka marker?
Yes, basically the Aruka marker is used for detection of kids. With the help of Aruka marker only, our drone is going to detect the kid. We know that this is not the optimized method. Still, better methods have been there. But according to the, we also read about some research paper also. But all about the availability of cost and everything, considering into this mind, we found this optimal approach. So yeah.
Okay, thank you.
Thank you.
Now, in many areas, such as delivery of goods, the creation of maps of the area, the rescue of people, the use of gasoline transport fuels, which is due to developed infrastructure for it, roads, technical stations, services, and the most importantly, gas stations. The advantages of unmanned aerial vehicles in these areas are obvious. High speed, exclusion of human factor, environmental friendliness, but the lack of infrastructure in our urban environment does not allow it implemented for daily use. 1 second. The biggest problem is the battery charge. The average flight duration of a commercial quadrocopter is within half of an hour, and the battery pack cannot be charged without a flight operator. With our project, we want to develop the infrastructure for the use of UAVs in everyday life, to develop a network of charging stations for drone operating in fully automatic mode. Since the use of charging stations over a large area is implied, it's necessary to ensure communication between charging stations and quadrocopters, to develop methods for selecting stations relative to quadrocopters using a single interface that combines stations and drones into a single network. Consider a real-time example. A quadrocopter performs an autonomous mission to deliver cargo. There are 5 charging stations in the area. The drone needs to charge its batteries. The current mission is suspended. The nearest fly charging station is selected. The platform extends. Landing is made of the current charging station. The quadrocopter is charged and suspendedly continues to fly. The goal of our project is to develop a prototype of an automated network of charging stations and drones. You can see the task of our project on the slide. The algorithm of our work. To cover the operation and basic principles of the network of stations, to make a prototype of a charging stations, to develop
I guess you may continue because
site, a small page and API. By pressing the documentation button, the user can get acquainted in detail with the work of an communication interface of the stations, connect his element to the system. Important, quadrocopter responds only the signals from those stations which they have access, which ensures the safety of installing such stations by several companies at once. On the live page of the live view page, you can monitor the current status of the charging stations connected to the system. Connection of additional charging stations is carried out in administrator services. The entrance to which is carried out with a password. Also, there is a gallery that includes photos and videos of the station. On the slide is a functional diagram of the charging station. The movement of the platform, the centering of the drone is performed using stepper motors. Indication of the current state of the station is carried out using a LED strip on the inside of the canopy. VMS D1 and Arduino Mega microcontrollers are used to control the station and connect stations into a network. To do this, HTTP requests are sent to the server. Changes are tracked between the current state of the station and the necessary change on the site. If necessary, the station change its state. The station model was developed in the Compass 3D program. First, landing skis were made along which is a drone is centered, then the canopy and a retractable platform. The parts were made from 3mm plywood on the Lyceum machine and from PLA plastic on a 3D printer. We also develop coax Clover program to land and some mission to test our stations. The server part, landing page, and API was developed in the Python programming language using the Django framework. With its help, charging stations and drones are combined into a network. 3 stations are selected in the relations to drones that need charging. Demonstration of work. The quadricopter informs the site about the need to charge the battery. The nearest charge station returns its coordinates. The platform and the charging station extends. The drone is expected to land. The quadricopter saves the state of the current mission for its further restoration, makes an autonomous landing and the charging station. The station changes. The station charges the battery. The quadricopter continues its flight. Conclusion: an autonomous network of charging docking stations was created. An algorithm for autonomous flights of the coax Clover quadricopter was developed. Communicated between charging stations and drones was organized using the API. I'm ready to answer your questions.
Okay, thank you very much. Okay, I will be the first. Please tell us, have you tried with GPS and will it work with GPS outdoor?
Okay, we extend our API to use not only Aruka markers to land. Also, we can change that field to GPS location.
In this case, what about precise landing? It will be some type of mix, GPS plus precise landing to Aruka markers, or how it will work?
Okay, the Aruka marker is on the station to land perfectly on it. It's small, then quadricopter can see it from 25 centimeter height. We can mix it and use for commercial programs.
So this Aruka markers quadcouples can be seen only from 25 centimeter of height or more than 25 centimeter of height?
Lower than 20 meters.
And if quadricopter is upper than 25, more high, so how it should navigate?
Quadricopter can see it from 1.5 meter to lower than 25 centimeters. It's
from 1.5 meter.
It's 35 degrees camera on Clover, I think.
Okay, but I mean, in this case, when you use it indoor, it's more simple case because quadcopter navigate on Aruka markers, and then it see your Aruka marker for landing and it lands. But if you use GPS outdoor, you have more problems with the height because you use different navigation system and different the different maps, different navigation systems, and it interesting how quadcopter will change from using GPS to using your markers and back maybe, and so on, and what high it will work. So I understand you didn't try it, but it's not such easy as you think probably. It could be some issues with this.
I don't test to mix GPS and the Aruka markets, but the server can but the server have these functions to mix it, and we can, GPS get locations for about 10 meters. We can use bigger Aruka market to positioning drone, and then use a smaller market which is on the station.
Okay, and the last question from me, please tell us about charging. Will quadrocopter charge and how it works?
It is the contact charge. The quadrocopter has special contacts, and other is on the station. The platform move into the station, and quadrocopter connects these contacts.
Is it 2 contacts or 4 contacts or 5 contacts?
Use 3 as batteries, then we use contact charge with 4 contacts.
So it's 4 contacts for balancing charging, right? And how you know when charge is finished?
We use a microcontroller for charge, and then which is controlled with Arduino Mega. Then set the signal for VMAS the one, and send information to the server.
This Arduino Mega connect with the Raspberry Pi or directly to the server?
Directly charger. And
no, I mean it connects to the Raspberry Pi.
Mega is on the station, not connected to Raspberry.
On the station, and it sends a signal to the server directly.
Yeah.
So you have Wi-Fi or 4G connection on charging station, right?
Yes.
Okay. Thank you.
Thank you. Second question from Andrei.
Yes, the time is almost up. So I wanted to ask, how do you dock this charging contacts? Because drone can land in different spots of the pad.
Okay.
Yeah, and also, do you have any mechanical CAD files for charging station open sourced, or did you open sourced only code for Arduino Mega?
We open source of the server. It is on the QR code on the site. This is a link of the GitHub organization, which contains an API and code for VMAS and Mega.
Yeah, so no drawings of the charging station to assemble it, yeah? Only the code.
Schemes of charging station are also there.
I just can't see them. In which repository are they?
It is on the site. If I don't delete it, commit.
Okay. And about charging pads docking?
Charging pads aren't open source, but we work with it.
Yeah, but can you show photo or the contact itself? How do you achieve docking given drone landing in different spots of the pad?
Of the different spots, we send a drone with
yeah, 2 rails. Yeah, I see. Okay, thank you. Okay.
Next question from Oleg Kochov.
If I understand your code and your documentation correctly, then you use pretty simple algorithm for landing, like you just use Clover's function to navigate relative to some marker, and that's it. And I think that landing is the most crucial and the most difficult stage and problem in making a charging station. So my question is, what is the success rate of your landing? I mean, how much tests have you performed, and what is the rate? Is 100% success or 50% or something like that?
It is only an example, and we use the while cycle from Python to a successful land. So we call this function such many times that we don't achieve successful landing.
No, you have a video of successful landing, right? So you had successful landing.
Yes.
Yeah, but how many tests have you performed, and what is the rate of success?
We tested only in indoor place.
Yes.
And if Raspberry yes, if drone is correct and can achieve success work in other algorithms, indoor we have 99% success landing, and for outdoor the drone performs while cycling.
99, but how many tests? Was it 5 tests or 50 tests or 100 tests?
We tested about 20 times.
And 99% was good.
Yeah.
Okay, that's pretty cool for such a simple code, such a simple algorithm. Okay, thank you.
And final question from Alexander Fomenko.
Yeah, so as Andrei said, the time is almost up, but the team was ready to start on time, and we started later, so we still have maybe a minute or two for the question, right? We're talking about lithium polymer batteries, right? It's like traditional drone, correct?
What's question?
So we're the purpose of your station is to charge lithium polymer batteries, right?
Yes.
Okay, so the drone, you've mentioned drone delivery as one of the main operations to support with your drone station. So drone delivery has two major problems here. So to deliver cargo, we mostly use one battery or one set of batteries for one delivery, because delivery, it is always like 1 mile, 2 miles, even maybe more than 2 miles. And to deliver like 1-2 kilograms of cargo, we need one battery, no more. So then the question is, who loads the cargo? So because if the cargo is loaded automatically, so your station needs to be not just charging the drone, but also loading the cargo on it. But if the cargo is loaded by the human, so the human can replace the batteries. So what's the point?
The current station is located is on the roads of quadrocopters. That's small animation. The quadrocopter use it while performing that mission. Don't in the
I think. So I'm just saying that the energy of lithium contained in lithium polymer batteries is so small so that it's barely sufficient to perform the delivery, and it does not sound reasonable to waste time for additional landing and takeoff just to charge it. And then the second problem is that in drone delivery operations, you don't have a time to waste to charge the battery. You need to perform as many deliveries per hour, per day as possible. And from this point of view, you don't want the drone to be sitting idling on the charging station. Yeah, that's it. Like I'm working in drone delivery right now, and we're targeted towards hundreds of deliveries per day. And to reach this goal, we will be swapping the batteries manually when loading the cargo manually as well. And if it's like automatic load of cargo, it's going to be a different place where someone swaps the batteries as well. Or it might be an automatic battery swap station. But again, in any commercial aviation, the aircraft needs to be flying, not sitting on the ground. And otherwise, it's not like viable or scalable. That's what I'm saying.
The second step of our project is to create the stations, which is switch battery.
Yeah, that's what I'm trying to say. Yeah.
Thanks for your idea.
Yeah, or it will be a hybrid drone, which is completely different story, and you need to charge to load hydrogen in it automatically, but not like I'll charge batteries. Thank you.
Yeah, thank you very much. And meet our next team, Clover Cloud team.
Hello, can you hear me?
Yeah.
Okay. Hello, everyone. We are pleased to present your Clover Cloud platform. A platform that allows you to work with Coex Clover quadcopter simulation right in a browser. Our project was created from scratch without using ready-made solutions. The main task that our product solves is to eliminate the need to install and configure a virtual machine, as well as the use of a powerful computer to work comfortably in the gazebo simulator. One moment. Okay. Our team includes team leader Kirill Ishinsky, front-end developer Mikhail Kuznetsov, and backend developer Daniil Valishin. On the slide, you can see our contact information. Our team has already had a successful performance at CopterHack 2022, where we presented the Clover Rescue project and took third place. Today, we are proud to talk about our new project, presenting its technical component and taking a detailed look at all components of our product. We use the JavaScript language along with the React framework to create the site. The design is made in the style of material design, which allows us to create the most convenient and intuitive interface. The source code of the site is stored on the GitHub. Building and deployment to Firebase hosting is done using GitHub Actions. Interaction between the site and the server is performed using WebSocket technology. Okay, let's look at our server structure. For programming language, we choose Python because it's a very scalable and simple language with many libraries for our project. Main advantage of our project is several script structure. Main script handles user requests and provides communication between the other scripts. Subserver. There can be any number of subscripts, and they can be installed on different servers. Through the Palex library, they manage containers. There is also a container script that manages the simulation and streams container data. When you go to the home page, you can see general information about our platform. From here, you can go to the registration or login page. Our platform uses Firebase authentication system. This hosting also stores user data in a secure form. Firebase allows us to authenticate users not only through email and password, but also through third-party providers. So you can log into our site with a Google or GitHub account. After registering, you will be taken to a simple and intuitive workspace management page. Each user can have a maximum of 2 workspaces at a time. All requests to create, start, stop, and delete instances are sent via sockets to the main server, which redirects the request to one of the sub-servers. After creating a CS instance, the user can go into the workspace of that container. And this is the main part of our product. The simulator itself is not enough to work fully with the simulation, which is why we provide the user with a set of tools for working with the drone. Let's take a look at each component separately. Let's start with the file manager. This is a component we created that allows the user to work with the container's file system. To get a list of files, a request is sent to the server containing the ID of the container from which we need to get information. Then the main server searches among the containers connected to it for the right container and redirects the request to its container server. The server scans the directories and sends the file list back to the site, where it is rendered. The next component we will look at is the code editor. It allows you to view and edit any file, and it also has syntax highlighting. It is based on the Monaco editor. Just like with the file manager, it sends a request to the container server and gets the content of the file. It also has the ability to view images and markdown files. And next is the terminal. It is written from scratch and supports output highlighting. Executing commands from the terminal is implemented using TTI technology. And most importantly, the simulator itself. We didn't use ready-made solutions such as Gazebo Web because then we wouldn't have been able to implement a convenient Aruka map editor and the environment editor. We can't run the simulation in the browser, so this component only visualizes data coming from the Gazebo simulator, which runs on a container without a GUI. When it runs, the container script receives the Aruka marker map and the list of objects the user has added to the simulation and launches the telemetry stream.
Now, more about the world editor. The user can conveniently and quickly change the position and ID of markers on the map, replace markers with PNG images, as well as generate new markers. All changes are written to the marker map file, then Gazebo simulator. World files are updated. Changes take effect after restarting the simulation. The user also has the ability to add and edit groups in the simulation environment. These groups are created and loaded directly into Gazebo world files. So unlike the original tool that to add objects to the simulation scene, they are not lost after rebooting the simulation. Our platform also provides a template system. All users can share pre-configured containers, just like in Code Sandbox. Once a user published a template, all other users can install it in their workspace with a couple of clicks. So far, we have created several templates that offer code example for some tasks. Our main project development plans includes switching from several files to Kubernetes and Docker for more efficient container management and platform scalability. This will allow us to manage resources more flexible and provide more stable and reliable operation of our platform. In addition, we are actively working on improving the security of our platform and expanding the functionality of our platform components. We are confident that these development plans will help us continue to improve and enhance our platform, providing users can with convenient and relatable tools for working with Clover quadricopter simulation. That's all. We are ready to demonstrate the work of our platform in real time and answer any question about our platform, its structure, functionality, and technologies that we use.
And we can demonstrate in live working with our platform. Now, let's demonstrate the screen. Do you see the browser?
Yes.
Okay, I will create one instance, for example, workspace. Okay, I can run it. Okay, there is a workspace page. Now I can install one of our templates. Installs now. Okay, and I can run an example script from the competitor. Oh, sorry, I forgot to start with the gazebo. We need to wait a little, and there is John with a book. And one moment, and I can run the script. And as you can see, the copter starts flying. In circle. Right in browser with a lot of frames per second. Okay, and in the itlets. So we can answer your questions.
Yeah, thank you very much. It's really great, and it really works, and it's very great. And the one thing I like the most is very simple. It is very simple, easy interface, very easy to understand, and very fast to get in. So just logging with Google account and start to run simulator very fast. It's very cool. I have a question about your server and power on your server side. So where is the server located, and how many users can run the simulation simultaneously, and what is the real-time factor, and so on?
Okay, we have servers in our school. They are not very powerful, but we can serve, I think, a very big amount of users. We tested it and we ran it like...
Sorry, how many users? I misunderstand.
A lot of users. We tested it with like 8 or 10 gazebos running at the same time, and it all worked properly. But we can add one more subserver in other servers, so we can serve more big amount of users.
Yeah, and what can you expect the cost of one user per 1 hour probably of using this?
Because each container needs like 2 virtual cores of our server for the correct gazebo simulation. So no.
Sorry, I don't understand. I mean, if you rent some remote server, how much could it cost, and how much will cost per one user per 1 hour of working?
If we use hosting like DigitalOcean or Azure, I think like $3 to $5 per user.
$3 to $5 per user per what, per hour?
Per
month?
one core and
per month.
Per month.
Per month for one core server.
So it's $3 to $5 per user per 1 month for running 24/7, right?
No, I think it's it.
Okay. Thank you.
Do you have other questions?
Yeah, second question from Alex Lukov. Sorry, turn on your microphone.
Yeah, of course. I'm sorry. Thank you for your presentation. It was very interesting. And I just have a question about your plans. What is your vision? How you see your project in 1 year or in a 10 year? What part of your product you want to develop, and what are you thinking?
We want to scale our product for many users, and how I say, we want to move our server structure from several files to Kubernetes system. It's help to improve for
the
user experience.
Okay. Maybe next question.
Yeah, Oleg Kalachov, your turn.
Yeah, my question is about what is actually an instance or on your system? I mean, do you create a Docker container or just different processes that run in one operating system, or something like that? And how do you isolate instances from each other? And what would your system do if that's not enough resources to run more instances? Do you have some kind of automatic creating a new virtual machines in the cloud or something like that?
Right now we use LXC Linux containers for create our workspaces. Isolated containers. Linux containers is isolated from other containers, and right now we don't make system to shut down and remove all containers.
Containers management is done by automatic system. So if you click the run or stop or delete button on the server, just deletes or runs or stops the container.
But your system targets only one machine. I mean, it cannot be distributed to several machines in cloud, because one machine anyway has some limits on running instances. And I actually don't think this limit is very big, actually.
So we know the problem, and we created the sub-server that can be not the one. It just unlimited. We can create unlimited sub-servers, and on not only on the one server. So we can scale our platform for several servers.
You mean for now you have more than one machine?
Yes, yes.
And your system automatically takes the amount of machines based on the number of users that use it, right?
Yes, if you install our subserver for all the machine. And we have Google Analytics, and we can just see how many users use the platform at the time, how many instances created, how many deleted. And based on this information, we can scale our platform just in a few clicks.
And one little question about deploying the system to some kind of cloud service providers. Do your system require the machine to have GPU? Because almost all of cheap machines in cloud providers don't have GPU.
No, our system is not requires GPU because we use X server for simulation GPU.
But Gazebo that is running simulates renders the pictures from camera, right?
Yes, yes.
And it does it well without GPU.
Yes, yes. But we can run Gazebo on just on the CPU, and all the features will work properly, and we have no problem with that. But if we will have a server with GPU, Gazebo just will just use the little resources. Right now we are demonstrating. Second, please. Yes, so the squad will take a picture from the John's camera using this CV2.
Ну, сейчас они покажут.
Image.
Okay. Because one remark, there was similar projects for Clover, but they required GPU, and GPU machines were very, very expensive, and that was the problem.
No, but but our service don't requires GPU. We use just Linux containers without graphics output.
Okay, thank you.
Yeah, thank you very much. And now we will give the floor to the next team, FTL.
No, wait, please. One more final question. Can we help you to promote this project, or do you need some help from us to develop this project?
Yeah, yes, of course, we need help to promote it. I think the COEX community will appreciate this platform because it's just very simple and powerful tool for working with Clover simulation.
Yeah, I think so also. So just please send some promotion message to group, and we will like it, and maybe resend it to other groups and so on, with description of your simulator, with link to instruction and so on, something that users can easy to use in English and in Russian language as well.
Okay, I think it's very helpful. Thank you. But we need more servers.
We will
make it. So it's just a few clicks.
Thank you.
If you need more powerful server and it requires some money, you also can send me your request about this.
Thank you very much.
Okay, thank you. You're welcome.
Okay, thank you. FTL, are you ready?
Hi, can you hear us?
Yes, sure.
Hello.
Let I give you access to show your screen. Wait, please. Okay.
Oh, yes, 1 second.
Okay, great. We can see.
Is it seen? Can you see my screen?
Yes, yes.
Okay, cool. Hi, I am Max Romanowski from FTL Team, and I present our project Advanced Clover 3, the platform. This platform created by the construct called ROS Development Studio. It provides user with a way to learn ROS development from browser. The user is presented with a page where user can read tutorial, view simulation, and develop in IDE. And our project is what you can say ROS Development Studio, but for Clover. Our team participates in CopterHack for the third time, and Advanced Clover can be considered a trilogy at this point. Our first project at CopterHack 2021 was Clover IDE, that greatly simplifies development for Clover by providing IDE in the web browser with tools to interact with ROS and Clover. Then, at CopterHack 2022, we have created a project that simplifies launching of Clover simulations and provides a robust system of tasks. Now, this year, our final project of Trilogy, we have improved and integrated our previous projects into the ultimate platform for learning and project development. One of main concerns about Clover Sim version 1 from previous year was installation and setup process. Setup required running of scripts and was quite complex, especially on Windows subsystem for Linux. This year we have worked on this problem with Clover Sim version 2, and now installation process is just 3 steps, one of which is optional, and we also have great support for Windows subsystem for Linux. And we also have greatly reduced installation size from 12 gigabytes to about 3 gigabytes. The workflow for users of our platform is very simple. After user starts Clover Sim node, user should open the browser and navigate to Clover Sim web interface. Then user should create and select for space, select task which user is going to try to solve or learn, and then launch simulation. After simulation is launched, user will be presented with dashboard. It's on screen. On dashboard, user can stop, start, restart simulator, change randomization seed that defines how objects are placed in the world of this task, view task description or tutorial in case it is some learning course, for example, and open different tools, for example, Gazebo Web, Web Terminal, or IDE. Most users will work through IDE because it provides very nice experience. IDE is based on FIA and is very much like VS Code, but just better, especially for our use case. It has support for multiple features. For example, tools to interact with ROS, tools to view telemetry from Clover, tools to interact with simulator itself, and stuff like this. Yeah. Here is on slide is image of IDE when user is trying to develop something. You can see on the center there is a code window, there is support for the completion. Then on the right there is task description widget opened, where user can read tutorial or task description to understand what he should do. And on the left we have file manager. Then when user wants to test program, user can open additional views in there. For example, Copter status, as I mentioned, that allows to view telemetry and camera image. It's in center. Then on the right, there is simulator control widget that allows the user to view his current score for tasks. Tasks are automatically checked and user can see in real time how good he completed his task. And also he can start, restart, or stop simulator and change randomization seed from there. And on the bottom right, you can see Gazebo Web directly in IDE, so users don't need to switch between different programs. Everything can be done from a single page. I will list more features. We have efficient simulation launch. We use containerization instead of virtualization, which provides much higher performance. Containers are executed, and actually with Clover Sim version 2, there is now a technical ability to launch multiple simulators, which will be useful if we are going to deploy our platform to the cloud and provide simulation as a service. Then there is ability to work with multiple projects simultaneously without need to create different virtual machines. Task systems provides ability to people to create different worlds. Worlds can have objects, they can have automatic task checking that checks how good user complete the task. And with Clover Sim version 2, which we developed this year, we have greatly improved experience of developing Clover tasks. Now there is no need to constantly restart simulator. You just need to press one button. And a new thing in Clover Sim is Web UI. We have created Web UI. Now there is no need to use command line to interact with Clover Sim. We also have created custom patched Gazebo web version that provides ability to dynamically load assets, because standard Gazebo web can only requires to know all assets in compile time, basically. And our Gazebo web also supports Clover Last Trip and ability to follow different objects, which is quite useful if Clover is flying on quite a big field. Then we also have improved our Clover IDE. Yeah, as I already mentioned, Clover IDE is similar to VS Code with mainly support for C++ and Python, but more languages can be supported by installing extensions. There is auto-completion and auto-formatting. There are tools to interact with ROS, topic visualization, service calling, and image topic visualization. There is Copter status that allows to view telemetry for Copter. This year we have added ability to view Let's Strip from there and also improved the design a little. And totally new tools that are Clover tools to interact with Clover Sim, like simulator control. I have already shown it allows user to view score, restart simulator, and change randomization. Task description allows user to view description of task. It's written in Markdown. There is support for images and stuff. And Gazebo web, as already shown. Another important part of our project this year is Clover Sim course. Clover Sim course includes multiple lessons to learn basics of working with Clover. We have created this course to focus on different aspects that are very important in Clover-based competitions. For example, NTO, Innopolis Open Robotics, or Cup of Educational Robotics in Belarus. First lesson, of course, teaches the basics of Clover flying a square. It's very simple. It's also automatically checked. So when user runs code, it can see that user can see that everything he did is right. Another task is ICO. This task teaches user how to interact with camera. There is randomly generated QR code and randomly generated color floor. And the user needs to scan QR code and understand what color floor is it, send it to checker, basically to server. And if everything is correct, a user will get full points. Then there is land in the middle task, which is inspired by part of task of Innopolis Open Robotics 2020 competition, where in this task, user needs to land on randomly positioned landing area. Then there is fly by line task. In this task, user needs to fly along the line. It's also automatically checked. Actually, all the tasks are automatically checked, and all of them except first one have some element of random to greater check task. This task fly along the line is inspired by NTO Flying Robotics 2022 and the Belarusian Cup of Educational Robotics. And final task right now, we are planning to add more tasks, but final task right now is position known. In this task, user needs to fly around the Aruko map and detect position of different markers. This task was also inspired by Innopolis Open Robotics 2022. Now to the demonstration. Can you see my screen now? You should see Clover Sim Web UI.
Yes, yes.
Okay, good. This is Clover Sim Web UI. On the left, you can see workspaces. There is quite a lot of them. I use Clover Sim quite oftenly. Then on the right, there are tasks window where users should select task. I will create new workspace. It's done just with multiple clicks. Then user selects workspace, selects tasks. I will select fly by line tasks and launch simulation. After some small amount of time, one second. Can you still see my screen?
Yes, yes, we do.
Yeah, okay. User is presented with the dashboard, as I mentioned. On the right, there is task description, which, because it's a learning course, includes step-by-step tutorial with steps to implement something. Task scoring, which shows how good user have completed tasks, and ability to control simulator. There are also tools, Gazebo Web, Terminal. User can also connect with SSH if he prefers to. but I will open IDE as it's one of the most interesting parts of project. Now I will open some folder. So when user open IDE, he probably wants to start. Oh, I actually have some stuff open. 1 second. I will close it. I will create main.py file and open task description to understand what I need to do. As I already mentioned in the step-by-step tutorial, but I'm not going to follow it. I'm going to skip to the end. Copy final code. Insert it to main.py. Now I want to try and check this code. I will open additional tools like Copter status to view what Copter is currently doing. Simulator control, which will show me status of simulation, and GazeWeb. I will place it at the bottom. One of cool features of FTL that, unlike VS Code, it allows you to, for example, split terminal with other windows than terminal. So I can have this very neat layout. So I will run this code. As you can see in GazeWeb, drone is taking off. Last trip is highlighted with purple color. And we can see that when drone moves along the line, we get more points because the further we move along the line, the more points we get. It will take some time, but when it will arrive, we will get full points. So that's experience that our users will get with Clover Sim. I will keep this running. Now back to, we also have some plans for the future. One of the most important ones is to add more lessons for Clover Sim course. I actually, when I was creating this presentation, I had an idea of adding joke task offline directly into the ceiling as sign of our command. Then we also think about providing our platform as a service that is accessible online. User pays some money and can run simulations without installing anything. That will provide more convenience. And also we would like to make Clover Sim more an official way of Clover simulation, add some articles to book about it, and maybe promote Clover Sim course. That's all. Thanks for attention.
Yeah, thank you very much. It's awesome, very great project. And I like this example with flying through the line, above the line. It's very great. So as I understand correctly, you have the whole course that explain how to code this program, right? So to code this line recognition and flight.
Yes. For example, 1 second, I will make screen a little bit bigger. You can see there is definition of task if user wants to try to do it by itself. And then there is step-by-step tutorial that explains the ideal algorithm. Then it teaches different things that the user needs to do. It shows how to do them. It shows how to detect line, how to understand how it's located on image, how to turn this information into velocities needed to control copter and everything like that. And that's for every single lesson. And of course, there is automatic checking of them and randomization. Okay, I will show it a little later.
Yeah, it's very great, very cool thing. So yeah, I think it's a good idea to have some course, online course. So you tell that it's possible to make software as a service solution like a previous project to run it total from the web, right?
Yes.
Anything?
Yes, that's right. Clover Sim version 2 have a technical support for it. It will require some small code changes, but it's not really hard and possible to run.
Yeah, I think it's a great idea to have a course, online course, probably some more basic course for free and a more advanced course for money.
Yeah.
And
that was one of the intentions. Our courses can be easily distributed. It's just users. It's much easier to distribute them because it's basically a zip file. But that's all.
Okay. Yeah, but anyway, if it will be online, it will be easier to create some payment model, freemium model. Yeah, something for free, something for payment.
I agree.
I think it would be more easy than something to install on computer. And also it will be more easy to users to start with it without installing anything.
Yeah.
Okay, but anything, anyway, the project is great, and I like that you want to make a course, not only a tool, but the whole educational course is great.
Yeah, I actually wanted to add one thing about cloud simulation. We actually checked it with my friend. I was using my PC as a server, and my friend was connecting from completely other location on the internet with Cloudflare tunnel, and it worked great. Any more questions?
Yeah, next question from Andrei Krypotsky.
Yeah, thank you for very useful project for Clover. I think it's a great idea to make such online courses with simulation. Could you comment on the adoption of Clover IDE and Clover Sim? So we have Clover IDE for 2 years and Clover Sim for 1 year. Are there people who are using these tools? Thank you.
Yes, I can. Actually, I was helped. Some of the improvements in the Clover IDE and Clover Sim was suggested by one of the teams on Belarusian Educational Cup of Robotics. They use Clover Sim to test their programs and do stuff. So they suggested, for example, displaying of a LED line in the copter status. So yes, we
great, but we don't have any numbers, yeah. Like
no, I
100 users or
no, we do not have and the Google Analytics stuff like that, so I can't really say anything about it. It's just the stuff that I talked to people about, that I learned about when I was developing Clover Sim and testing it.
Okay, thank you. Great project.
Thanks.
And final question from Mikhail Smirnov.
Okay. In continue, maybe the same question. How many users in your system right now? Maybe it's member of team or any team's member in Belarusian. How many users?
Well, the ones that I know, it's definitely at least 2 teams. Although our country is quite small, so there is 4 teams competing in our competition, and 2 of them are using Clover Sim. But probably there are more. They didn't contact me, so I can't really say anything about them.
Okay. Okay, thank you.
And one more question. Question from Oleg Tolchov.
Yeah, I see that your project is kind of competitive to the previous one. Maybe you can provide some comments. What are the advantages of your projects? And maybe what is advantages of that project and your plans about it? Or maybe you want to unite with them.
Well, I believe I watched presentation of previous team. I believe one of the major differences between our projects is the way we work with Gazebo World. They provide a way to create more interactively by placing objects by users themselves and by placing users themselves. Our platform is more focused on creating more complete solutions. We also, unlike previous team, we have support for automatic checking of tasks. As you can see, it's automatically scored. And of the world is generated pragmatically. So in case of previous team, I believe I did not see an example of randomly generated worlds. In our case, we can generate worlds randomly. Actually, while I was answering questions, I restarted simulator with new randomization seed, and you can see that there is a completely new line. Then I believe there is also difference in ID we use. Our team uses Thea. It's more powerful, I believe, at least in layouting. We can move stuff however we like. We can use VS Code extensions, and that's, I believe, most important differences. And we provide an easy way. Well, it's very easy to run Clover Sim locally now.
And also about the comparison with the previous project, can I easily run multiple instances of this thing on one machine, or you don't work at it and you run only one instance on one machine?
Right now, it is possible to launch multiple instances, but there is a problem that they use same IP address. It's quite easy fixable with network namespaces, but we haven't worked on this feature. We mostly focus on tasks checking, developing of Clover Sim cores, and making that everything to work locally absolutely flawlessly.
Okay.
Thank you very much. And our final participant, Atena Team.
Hello, can you hear us?
Yeah.
Yes, hello, we do.
Okay, can I start the presentation?
Yes, try now.
Okay, thank you.
Okay.
Let me
You're
just
welcome.
start it real quick. Can you guys see it?
Yes, we
Yes.
do.
Okay. Hello. Now let's start the presentation of Team Atena's project, the Swarm Blocks. Well, first of all, who are we? We are Atena Team from Samir Group, a robotic group from University of São Paulo in Brazil. I'm José Carlos.
I'm Lucas Duarte.
And I'm Gabriel.
And we make up a team of 7 members.
Well, let's start with motivation. What makes our project useful and interesting? Well, let's imagine a hypothetical situation. You firstly buy the clovers, 4 or 5, for example. Later, you have to set up all configurations and connections between them. So you let up all full code for all clovers also. Just after all this, you can make the flies, tests, and monitoring in the swarm. As can be seen, the all flow is complicated to finally launch the swarm. Currently, you have already all programming abstraction with the first version of Swarm Blocks by Atena Team, the winner of last year. So it's missing 3 of the 5 steps yet. Let's take a closer look at these steps. After buying it, there are a lot of procedures that are separating the Clover to the fly, since the Raspberry Pi is set up, like firmware download or configurations, onto the network and the connection infrastructure needed for each drone. In addition, it's hard to implement a communication and a control system for all alive drones flying coordinated. Imagine you have those 4 or 5 drones yet, and you want to send to them a period information, for example. You need to send each drone for each position one by one, and later again a new formation. For all these drones, we'll need to know. All these drones need to know where to go, knowing the path of others. Code all this algorithm is pretty hard. Sequentially, you have the system complexity problem. After all physical setup done, you create a terminal to launch nodes and services for the first drone, and later you do the same for the second, the third, the fourth, creating more and more applications. So, as can be seen, it goes for a mess, a pretty confusion system and control for debugging, for control and debugging. All this because the ROS and the Linux complexity, mainly for lay and novice users. Also, if you just turn off the clovers for a quick coffee break, you need to later to repeat all the process again for each swarm launch. So now we introduce the Swarm Blocks 2.0 and its applications that solve these all problems. It's never been easier to swarm. And here we have a quick demonstration of the swarm flying in a light. Here we see the sky black and a beautiful fly of the 2 drones coordinated flying with the LEDs and everything. Pretty beautiful. Beautiful. Well, coming back for that hypothetical example, now we in 2023 created and solved the rest of these pieces missing to complete the swarm launch, abstracting them to the easiest way possible. And here's the idea. The idea is centralized the ground in a ground station. It provides a more intuitive and a logic interface, achieving by consequence the novice and the expert users. At the end, the all application provides an easier coordinated control, providing a more safe and reliable fly by consequence. Finally, let's see this in our platform. All this is on the front-end architecture of the ground station and is divided in home page and its three childs. Here is showing the home page. The three childs are the swarm blocks, the swarm station, and the swarm FPV. The swarm blocks itself was already 98% created in 2022, and the swarm station is going to be seen now. Well, what is it? The swarm station is an integrated platform for full swarm monitoring, fully developed by us. It gives an easy and intuitive interface, have in just one place all centralized applications, all this providing a complete swarm access. In this web application, this is a web application and it's running locally on the master machine, not in an outside server. The swarm station achieves the same application in the same application, two types of user. An expert user that already have the knowledge, but now having new facilities for debugging, controlling, and monitoring, working together parallelly to the terminals. We're gonna see them later. And the novice consumer that can get introduced for the novice consumer that can get introduced for the Clover platform easily, as can be shown. Well, let's see some of these features and the main of them. In the telemetry screen is shown a position and connectivity of the drones individually. Also, we have the Raspberry Pi parameters. You can see here the information as CPU or memory usage and the battery level of the Raspberry and the drone. We have also the safe area. Now talking about the safety, it's more reliable to have a safe area where the drones land in the same instant that drone accidentally pass through the wall. In other words, the swarm station prevents that the drones that are flying on your front just goes away and strike anyone or anything getting over of this area. The web terminal. The terminal is also a web application built in the swarm station, giving possibility to expert users to pull outside packages into the swarm station and do anything that it was already up to do previously without the swarm blocks doing on our platform. With the swarm blocks 2.0, it's even possible to coordinate drones together as individually, because the user now can assume control of the Clover in real life with the first person view, as you can see here on the interface.
Well, so how exactly did we make it? Well, our solution consists in creating an API that allows the user to easily send commands to the desired drones. In other words, after establishing the necessary connections mentioned in our documentation, the user just have to import our API, and then they're able to write direct scripts to control each drone, either individually or simultaneously, without having to directly access the Raspberry Pi, saving lots of lines of code. It's worth mentioning that we also maintained coax pattern for the code. Imagine that you have several Clovers and you want to send commands to them, sometimes to all of them, sometimes to a few, or just a single one, all from a single computer. Well, for that, we need a way of centralizing the connection. That's why we need an access point to make all drones be able to talk to the master machine, but still leaving their ROS network untouched. Well, in order to achieve this, we developed the Swarm client and the Swarm server nodes. Let's talk more about them. On our architecture, we have a server running on the master machine that accepts connections from all clients running on each Clover. They are nodes that interact with the ROS network of each machine individually, thus avoiding conflicts. And as you can see in the schematic that represents this server client architecture on the slide. Also, this way, each drone doesn't know about the existence of other drones on the network and only accepts commands from the master, leaving the network a lot more clean and lighter. All drones receives all messages sent from the master, but only executes the ones that are directed to them. We made it this way so that in case a connection is reset during flight, the drones keep only accepting the proper commands without additional setup. To actually send the commands, you just have to import our Python API. And for more instructions about that, you can go check out our documentation or our example scripts on our Raspberry Pi package on our GitHub. It's important to note that this is not the only way of doing it. For example, it's also possible to put all vehicles on the same ROS network, but doing that, you require to put every single application on its own namespaces, besides being unstable when it comes to network. That's why we chose the server solution. Here's some few more presentations of our results, and you can see that we've performed both indoor flights tests using Aruco map navigation systems as visual odometry, and also GPS for outdoor flights. And clearly, the GPS had the best performance and consistency for our system. So we really recommend using GPS if you want to fly a swarm.
To ensure the safety of the system, we have made a treatment to avoid collision between the drones. For example, in this three-dimensional formation, we had a lot of incidents which involved damage or falling of clovers. We knew that the risk of collision is very real, so we started rendering collision using an algorithm. The algorithm divides the collision into some cases, and for each different case detected, it performs a sequence of actions that prevents a collision from happening. With this, we acquire a high security to our system.
And that's how we solved problems we've listed regarding flying a swarm of drones. The Clover is a really great drone for our application because it's open source and really practical, and its applications are very flexible. So that's our project for CopterHack 2023, the SwarmBlocks 2.0. But the work is not done yet. We still plan to continue SwarmBlocks development to bring the most complete version of our solution. For that, we plan to apply our application on real-life situations where swarms are needed in order to validate our platform even more. Also, our collision avoidance performs really great on simulation, and that's why we plan to validate it on real-life flights to demonstrate its importance, of course. Lastly, we still need to improve our main network structure to make it more robust and reliable. We are Atena Team, created a SwarmBlocks platform, and we thank you all for the attention.
Okay, and first question from Alexey Shlukov.
Hello, guys. Thank you for your presentation. It was very interesting. Your system is very simple usage for drone swarms, and usually drone swarms using for some kind of drone show. Have your application some communication with music part? Do you using timestamps? Can your drones, your swarms synchronize with music?
Yes, it is possible because you can send direct commands to to all the clovers at the same time. So you could write a script that could synchronize a song that you're trying to present with information. That is really possible, actually.
Yeah, thank you.
And second question from Oleg Kolachov.
Okay, the first question is kind of a basic. You run some server on a separate machine, right? And this machine generates separate codes in Python for each drone and send it to the drones, and then drones execute this code autonomously, or it work different way?
I think it's a bit different than what you said. The Clover executes our commands in real time, so we don't send like a script to the drones. We could. This actually, we thought of this way because if the drone loses its connection to the router, it would still execute its path and its command. But for now, the drone must keep connected to the router, and you send direct commands to them so they respond in real time.
Mm-hmm. Other question is, swarm and show actually is more than 2 drones. Have you tried maybe this with more than 2 drones, or you don't have more than 2 drones?
Yes, that's actually the exact problem that we have. We don't have more than 2 drones. We just have only 2. We did last year a lot of formations using several clovers. I think up to 20 to 30 clovers on simulation. It worked really great. Actually, that cube formation we've shown for the collision avoidance is on a simulation. So it is possible, but we still have this limitation of the amount of clovers to actually show the full potential of the platform.
Can you maybe combine real drones and simulated drones in one scene, or it's impossible, or you haven't thought about it?
It is possible. We kind of do this already, because the Storm Station picks the body frame of each clover and publishes on a homepage. I think it'd be better if I show you this. So yes, it is kind of a simulation. It's like a digital twin, we call. For example, here. This is a simulation example, but the clovers are running on a background, but still our platform can see and listen to their position and their status. So yeah.
Okay, and what is the main achievement that you have achieved from the previous year? What is
From
the
the
greatest
previous year?
and what is the greatest addition?
The greatest addition, we have on our Gitbook, we have a session just telling what's new from the last year, because we knew. But the Storm blocks is already done from the last year. And so this year we worked on the Storm Station that provides the Storm FPV underground station and the real Storm. We did the ground station on that runs on web. We recreated the Storm FPV, and we made the Storm fly in real life.
Okay, great. Thank you.
Next question from Andrei Kurigotsky.
Yeah, thank you. I was very glad to see your drones flying. Can you elaborate about how do you send commands on drones and in what format? So is it Mavlink packages or ROS messages or something different?
No, it's actually quite simple. We just, let me pick the slide. It's easier to demonstrate here. Each Clover has a node that we call it the Storm client, the Clover client, actually. This client connects to the main server running on your master machine, that'd be your computer, the computer that from the user that it is sending commands to the drone, over TCP, over local network. We program that to make it easy for us. And we established a really simple protocol that contains the ID of the Clover, the command, and the parameters. So whenever you want to send the Clover some command, you go import our Python API, like I showed here. Import a Python API, create an instance of the ID that you want to establish the connection with the drone. And you just call like clover0.letEffect and our API.
Yeah, okay, so it's a web interface, yes?
No,
how do they communicate? Or just TCP IP?
This is just TCP IP. The web interface is just for monitoring.
Okay, thank you.
Next question from Oleg Panfilonex, sorry.
Yeah, thank you guys, great project. And glad to see you again this year. I'm wondering, you have tried flight outdoor using GPS, but no RTK, right? Only just regular GPS.
No, only regular GPS.
And how is it enough for precision or not for Clover Swarm? What do you think?
Well, we had interesting results. I can show them again to you. We have them here. We had interesting results. This is completely with GPS with the Clover firmware to the PX4, and it is quite unstable sometimes, but overall it's a great precision. I really performed really great. way better than the indoor.
Yeah, because it's hard to understand just watching only two drones,
Yes.
how it precise. But if it's really works, maybe it's could be really a solution for real swarm project. I mean, for some business regarding swarm drone show or something like this, because your system looks good, and maybe it could be also possible to use. Maybe do you have some plans for make a real drone show with it or not?
Yeah, it'd be really interesting. Our limitation is the amount of Clover, but it'd be really interesting.
Yeah. Okay, nice.
And final question from Alexander Klimenko.
So on this video, were they meant to actually hover next to each other, or they were meant to go like this?
They were meant to be switching heights. This was intentional. Like we programmed them to keep switching heights. You can see that they switch at the same time. So
so the drone on the right has a lot of horizontal movement. Is this due to bad GPS? I mean the GPS threshold. Okay. Okay. So I have a question.
I'm sorry. Can
no, you see. Oh, I can see what.
No, I was just saying. You can see that after some seconds, it stabilizes in its horizontal
I could see that. I could see that. So would you tell more about avoidance? Because I could have sworn that in your article I read about that you engaged the avoidance, mid-air collisions between drones. Is this correct?
Yeah. Yes.
So you can program the swarm so the drones have lots of collisions in the programmed, but they will automatically avoid all of them, or what?
Yes, the collision avoidance algorithms acts in real time, so you don't have to plan the trajectory first. You can send whatever formation you want, and it'll be constantly checking if two clovers are near enough each other to treat as a collision. So.
So how does this collision avoidance work? What sensing are you using for this?
Sensor.
Is there sensors, or I mean, is there a feedback from the real position of the drone or not?
Yes, we have to have some sort of feedback from the real position. We have to have the precise position of the clovers, and it works by, it's a node that runs on a master machine that keeps receiving the position of all clovers and checking 2 by 2 if they're near enough to treat as a collision. If they are, it has 3 cases: the stationary collision, the parallel collision, and non-parallel collision. And the algorithm does sorts of things to handle its possible collision depending on which state it declares.
And
for example, in
this
case,
keep going.
In this case, it is a non-parallel collision on the GIF.
And what's a parallel collision?
Parallel collision?
Yeah.
When the two trajectories are parallel, for example, like this.
Oh, okay.
And non-parallel transversal, for example, like this. It's
So,
easier to treat when you separate.
Yeah. So okay. And which sensors are used to determine the precise position?
That depends on what kind of odometry you're using. For example, if you use with indoor Aruku, you could use the vision position estimate. On GPS, it is a little more difficult to say that because it's the global position. The precision is not that.
Okay, and thanks. And lastly, did you fly with 3, 4, or more drones?
No, you only have 2 drones, 2 clovers.
And may I ask why?
because we can afford to have
Okay,
more.
you just don't have more.
Yes, we
Okay,
don't have more.
thank you. I get it.
And one more question. Mikhail, your turn.
Oh, yeah, maybe if just to clarify, does the simulation take into account the external factor, for example, the weather or anything else?
I'm sorry, I didn't understand the question. Could you repeat it,
Okay,
please?
does your simulator take into account the weather or any external factor?
Does the simulation take account of what?
The weather, meteor condition, wind.
The
rain.
weather. No,
Yeah.
no, the weather condition. We don't have a feedback for
no.
that. It'd be interesting to put though. It's a great idea for swarm manipulations.
Actually, I have to add that actually Gazebo has wind simulation. If it's enabled, then it's very easy and very trivial, but it has something like that.
Yeah. Yes, it'd be interesting.
Information about the sponsor of prizes. This year, the third place will be rewarded by Promauto company, and another places will be rewarded by COEX company. And now we are ready to announce results. And you ready? Okay. Fifth place is C305 team. Congratulations.
Yeah, congratulations to C305 team with the third place.
Thank you very much.
Good luck, guys.
Yeah, and the prize for the fifth place is $500 US. Congratulations, guys.
Yeah. Next place is fourth place, and fourth place rewarded to Atena Team. Congratulations!
Yeah, congratulations to Atena Team.
And prize $500.
Yeah, well done.
And third place. Third place rewarded Clover with motion capture system. Congratulations.
Great work.
Thank you.
The price is $1,000.
Thank you very much. I appreciate all the help and support from the Clover community. It's amazing. Awesome.
Yeah, thank you for your great work.
Second place. Second place rewarded FTL Team. Congratulations.
Yeah.
Thanks.
Yeah, great work. And let's continue to work together with the courses also. I would like to do something useful together.
Actually, we would also like to get some help from COEX. I know that COEX has S3 infrastructure to host Clover images. We would like to host Clover sim based image with Clover images.
Yeah, we have DigitalOcean
Yeah.
infrastructure, as you said.
And third place.
Yeah, wait. The price is $2,000 US for the second place. So congratulations.
And the winners. First place rewarded Clover Cloud Team. The prize is $3,000.
Thank you very much. Thank you. Really
Yeah,
appreciate it.
great guys. You're the best. Well done.
Awesome project.
Thank you very much.
Put it on your resume.
Would you like say some words?
I don't know what to say.
Yes.
Just wow. Thank you.
Okay, maybe our jury say some words for our participants.
Yeah, thank you, Elena. Yeah, the prize for the first place is $3,000. So I hope this money will help you to continue develop your projects. And also, I would like to work with you together. So let's stay in touch. Okay, so my final words. I'm just very glad to see your projects and especially glad to see a lot of teams that participate not only the first time but already several times before, maybe second or third times today on this CopterHack. It's really great and great to see your achievement year by year. So I would like you continue to work on your project and also think about new projects, maybe in other projects with drones, and please share your results, share your project in our community, in support Clover group, in PX4 group in Telegram, and in group with other in a CopterHack group and so on, and write me in Telegram, and maybe we can think about maybe we can work together to develop or promote your project. If you want it, I'm very open for communication, and hope to see you later on another events, and I would like to see some continued development of your projects, and wish you good luck with this, and maybe make some business based on your projects, business with drones, and wish you good luck with this, and thank you.
Thank you very much. We promote our project and those teams, those chats, but first we need to improve our servers. Thank you. Thank you.
Andrei, your turn.
Yeah, thank you very much to all 7 teams for your great work. I think it was the most interesting CopterHack out there. So also projects this year were just amazing, and I'm really looking forward to seeing what will become of them, especially for C305 project, because I think it's a very interesting field of indoor localizations of drones and simulation projects, 5th and 6th. I'm really looking forward into some integration with COEX ecosystem. I will be glad to see these simulators in use wide by COEX community. So thank you all very much. I will very glad to participate in this stunning event. Thank you.
Okay. Alexander Fomenko, your turn.
Yeah, I mean, to everyone here who is developing products and seeking for success in this field, I want to encourage you to not be shy to aggressively market and overprice your products. Because for the customer, the added value means that you're confident in what you're doing and how many years you have put in your education and your research and your development and all these efforts that you made on your products. And time is the most expensive asset in the model world, right? And years of time for the whole team of developing the certain product, it sounds expensive, and it should be expensive. And you shouldn't be saying that we spend that small money on the equipment or the parts that we build this project from. Like, it doesn't matter. Like, your customer is usually smart or a businessman who knows how much the parts cost for that. But what is precious here is your human resource that you put into your development. So, like, please don't be shy. And it should like I'm working in the industry now, and there's a lot of companies that we're partnering with or we're buying equipment from, and they're not being shy to charge us like not just thousands but hundreds of thousands of dollars for the equipment that the self value of which is like really low. And those companies are just pursuing their dreams, and I wish every one of you to be brave, and the Lady Luck will accompany you on this on your paths. So be bright, be simple, be representative, and sell how your ideas will expand the viability and usability of the products. So this is for the future. I wish you all good luck on this journeys. It will take years for most of us to become professionals and recognized experts in the industry. So thanks again for all the respected jury. Thanks, Lena, for careful moderation and organization of everything. And I want to say thanks to Oleg, who's hosting this event over the years, and it's been my pleasure to be a part of it.
Yeah, thank you, Alexander.
Thank you. Next turn is Alexey Shlykov.
Yeah, hello. Okay, guys, I want to say that you are, all of you make huge work, and you get to the end of this competition, and it's not so easy. So all of you are already the winners, and it's very important. Don't stop to create something new, and you have such a good experience at this competition. So continue create new awesome things, present them, sell, and get your $1 million and create your startups. You are already great teams. So also good luck.
Thank you.
Yeah, thank you, everyone. I'm glad that I'm a part of such an amazing event. And yes, I can only agree that this year's all the projects was really well done. There was in the final, there were no projects that were bad or something like that. I would like to mention separately projects about motion capture system and radio beacon system, because that's what we wanted to implement for a really long time, but we haven't access to motion capture systems, and we haven't got time to do something with wideband radio beacons. So of course the projects with simulation and with cloud systems are also cool, and every other projects was also well done. So thank you, everyone, and continue and go on your projects and your
I don't know, and your work. Thank you.
Thank you, Oleg. Mikhail Smirnov, would you like to say some words to our participants?
Okay. Yeah. Thank you, everyone, and my congratulations to winner. It was a very exciting year to see how you progress in your project, and Group of Promafta right now is just starting on UF market too, as you, and we have very interesting in any technology, and also we try to start the collaborative project in Nizhny Novgorod with the professional education for UF operator and UF engineer, and therefore they are very interesting with coax, maybe with some of the member of your team and we invite you to be a tutor in this project too, because we are very excited in your progress. Thank you for your participation. Thank you.
Okay, thank you, Mikhail. Maybe our participants would like to say something. Okay, thank you.
Maybe we can make a group picture together. Maybe you
sure.
could turn on cameras and make some final picture.
Yeah, please turn on your camera.
Okay.
Atena, yeah.
Okay, good.
3, 2, 1. Smile. One more time. 3, 2, 1. Smile. Thank you. Yeah. Thank you for cooperation. I have to acknowledge that the participants this year were the most responsible ones, and it was a real pleasure to work with you. I hope it was a fruitful experience for you. My congratulations. I would like to say thank you our jury for the work they done, and our participants for their brilliant results. Thank you. I hope we see you later.
Goodbye.
Yeah, thank you. Bye bye. Bye bye. Thank you. Bye.
Bye bye.